So we have come back to physics after a long time, and because of this long delay, let's just start by recalling some things. Let's start by recalling the notion of significant figures. So what happens when we make a physical measurement? That is, we use some kind of instrument or device and we measure the value of a physical variable in a given situation. Then our measurement contains errors, and this happens because whatever instrument we are using, it has its limitations. So when you make one measurement of that variable, the device gives you some digits in your measurement which are certain digits, and then you put some other digits which you feel should be there in the measurement but which are uncertain digits. So the convention is that you keep only one uncertain digit besides the certain digits, and all these digits, the certain ones and that one uncertain digit, they are called significant figures. For example, say you have a thin sheet of some material whose length and breadth have been measured using a meter scale, and these values were found. The length is 16.2 centimeter and the breadth is 10.1 centimeter. So you know that the way these measurements have been written, keeping that significant figures in mind. So we know that in this measurement, for example, 1 and 6 are certain digits and 2 is the uncertain digit. But all these 3 digits are significant figures. So there are 3 significant figures in this measurement. In the measurement of the breadth, also there are 3 significant figures, 1, 0 and 1, among which 1 and 0 are certain and that last one is uncertain. So now if one uses these approximate values which contain errors to calculate the area of this sheet, then one would multiply these two values. So obviously those errors also interact with each other, and actually we know what to do. We have gone through the rules for this type of things. Whenever we are multiplying or dividing with approximate quantities, the result should have as many significant figures as there are in the approximate quantity which has the least number of significant figures. In this case, both of them have 3 significant figures. So if we do the multiplication here, ultimately, mathematically you may get a value which actually does not simply have 3 digits. There may be more digits. But then we of course neglect the others, and we already know the rules for how to do that. But that's not the point now. The point now is this: rules for determining the uncertainty in the results of arithmetic calculations. So if we calculate the area of this sheet using those rules, then we will get some value finally. But what is the uncertainty in the area value? That we want to calculate now. So let's see how that can be done. To indicate the approximate nature of this measurement, 16.2 centimeter, we write it like this: 16.2 plus or minus 0.1 centimeter. Because 2 is the uncertain digit, we keep a room of 1 on either side of 2. That is why plus 0.1 or minus 0.1. But why 0.1 specifically? That is because this is the location of the digit 2 in this decimal representation of the measurement. That is why 0.1. Had this been something like 16.23, just saying, okay, then 1, 6 and 2 would have been the certain digits and that last 3 would have been the uncertain digit. In that case, we would have had to write plus or minus 0.01 centimeter. Okay, so it depends on the location of that last digit, what you write here. And then we express this in percentage. So this becomes 16.2 centimeter plus or minus 0.6%. And this actually is percentage error. which you obtain like this. If you forget this 100 for a moment, this ratio is the relative error. The absolute error is 0.1, and the absolute error is the difference between your ideal value that you should get and the experimental value that you have actually got. So when you divide that by the original value, the experimental value, when you divide that difference by the experimental value, that is the relative error, and multiplying that by 100, you get the percentage error. So this measurement contains this much error. So let us also see how much error the breadth value also contains. Similarly, so the breadth is this. Originally it's 10.1, but to show its error, we have also written here also, because this last digit lies in this location, so plus or minus 0.1 centimeter, just like the previous one. And in this case, when you express that as percentage, it becomes roughly 1% because of this. 0.1 divided by 10.1 times 100. It's not exactly 1%, but it's roughly 1%. Alright. Now, what about the area? In order to calculate the area, obviously you will have to multiply these two like you normally do, and then you take into account how many significant digits the result should have. 3, because this one also has 3 significant digits and this one also has 3 significant digits. But then what will be the error in the area? Can you calculate that from these two errors? Yes, you have to actually add them up. So let's do that and see what we get. So when calculating area, of course we just actually multiply these two values, and that way we get 163.62. This of course does not have 3 significant figures. The number of digits here is not 3. We have to make it 3. But before we do that, this much centimeter square, before we do that, we see the total percentage error also. So we add the percentage errors, 0.6% and 1%. So this becomes 1.6%. And using this, we can calculate how much uncertainty we have in this area value. So 1.6% of this turns out to be roughly 2.6 centimeters square. But then with this information, what are you going to write as your final result? Note that you should maintain the 3 significant digits, that thing here. So that means you should keep 1, 6 and 3, and you should remove these things. So recall your rule for removing or rounding of numbers. Because the first digit that you are going to remove is greater than 5, so the preceding digit should be raised by 1. So that way it will become 164. And what about this original errors 0.1? So there in each one, actually it's just 0.1. Turning it into percentage gave us something else, but originally it was 0.1 centimeter plus or minus. So there the number of significant digit is 1, and in fact it is that 1. Recall the rules for deciding the number of significant digits. Because it is 0.1, that initial 0, of course that's not a significant digit, but that 1, that non-zero digit after the decimal point is a significant digit. So for the errors, the number of significant digits is 1. But ultimately, after adding and after getting this value as the uncertainty in area, how many digits do you see here? Non-zero, 2. So here also you have to make it 1. And in doing so, you have to remove this 6, and that will turn this 2 into 3 because you have to raise that 2 by 1, and that way the final answer is going to look like this 164 plus or minus 3 centimeters square. So that 163.62 I think it was, that became 164, and that 2.6 centimeters square became 3. So that's how we have to write the final answer. And from this we can say this thing: if a set of experimental data is specified to n significant figures, then a result obtained from them by doing some kind of algebraic calculation like this should also have n significant figures, but we should not be so hasty in drawing such a conclusion because of what we are going to see next, where the number of significant figures will change. Do not forget that whatever we did in this example, multiplication was involved, and that is why the number of significant figures was determined by whatever rule we already had, namely that your result should have as many significant figures as there are in the approximate number or approximate measurement with the least number of significant figures. But if instead we have addition or subtraction involved, then recall that there is another rule where now the number of significant figures is not important, but the number of decimal digits is important after the decimal point. So if you are adding or subtracting some approximate quantities, then your answer should have that many digits after decimal points as many there are in the one with the least number of such digits after the decimal point. So let's see what that is. Let us look at this subtraction. A mass value of 7.06 gram has been subtracted from another mass value of 12.9 gram. You can see that both these approximate values have 3 significant figures. So the situation is just like that area, but this time we are not multiplying or dividing, we are subtracting. So the rule for deciding how many significant figures the answer should have is now different. How many digits does this one have after the decimal point? 1. This one, however, has 2 digits. So the final answer should have actually 1 digit. Instead, if you just do the mathematical subtraction, you get this value 5.84 gram, and in fact I have written, but since we are using approximate quantities, not qualities, the final answer should have only 1 digit after the decimal point, and that is why you have to make it such a number, and for that you have to remove this 4, because you are removing 4, so again that rounding off rule comes, which is less than 5, nothing happens to this 8. We do not raise it by 1, 8 just stays 8, and that way we get 5.8 gram. So you can see that in spite of both the approximate quantities having the same number of significant figures, the final result has only 2 significant figures instead of 3, because subtraction is involved. However, if multiplication or division is involved, then that thing is true, that if you have n significant figures in all your approximate quantities, then your final answer should also have n significant figures. Alright, next, the authors draw our attention to this fact: the relative error in some measurement depends not just on the number of significant figures that the measurement has, but actually on the measurement itself. For example, you have this approximate mass value measured using some kind of balance or some equipment, 1.02 gram. So if you want to calculate the relative error, and one more thing, the authors are calling this itself relative error, but I said that this is the percentage error. The actual relative error is this ratio. But some people call it this itself relative error expressed as percentage. Okay, it's just simply a matter of multiplying or not multiplying by 100. That's just it. Okay, so the relative error in this measurement is approximately 1% when expressed as percentage. Whereas this other mass measurement is 9.89 gram. So you can see that in this one also we have 3 significant figures, in this one also we have 3 significant figures. In spite of that, the relative errors are different. Here it is 0.1%, it is smaller than this one. Okay, so it depends not just on that number 3 of significant figures, but on the actual measurement also. And finally, there is one more point, and that point is this. Let's see what it's saying. The intermediate results in a multi-step computation. Say it's not like calculating an area of something where there is only one step. Say you have a complex multi-step calculation involving approximate quantities, of course, and the intermediate results, that means at every step you are going to have something calculated, right? And then you are going to the next step, so there you have some other calculation. So the intermediate results in a multi-step computation should be calculated to one more figure than what? In every measurement than the number of digits in the least precise measurement. That means, so you have some approximate quantities. It's not necessary that each time they all will have the same number of significant figures, that we already know. So you pick that one which has the least number of significant figures. And then the others have maybe this same number of significant figures or more significant figures. At every step of a multi-step calculation involving these quantities, say for the sake of specificity that the least precise measurement has 3 significant figures, you do every step with 4 figures. Okay. Let us see what happens if we don't do this. If we don't follow this rule and say the smallest number of significant figures involved in our quantities is 3 and we use only 3 significant figures, something will go wrong. Let us see. To keep things simple, say our calculation actually has only one approximate quantity and the value is 9.58. So you can see there are 3 significant figures, and what are we doing with this? We are calculating first the reciprocal of it, keeping in mind that our answer, whatever we write here, should also have 3 significant figures. So the actual division will likely give us many digits after the decimal point, not just 2 digits, but from that we round off and do all the other things, and ultimately we get this value. This 0, of course, which is before the decimal point, is not significant. So here also we have 3 significant figures. Now what was the advice that we saw here? That we should keep one more figure. We are not following that advice here, So we decide to use only 3. And then what we do, say this is not where we stop, but actually we then take the reciprocal of this. So the reciprocal of a number mathematically is equal to the number. Now what will happen if we take the reciprocal of this, keeping that 3 significant figures in mind? We find that this time we are getting 9.62. Okay, after doing the division, after rounding of everything, we are getting this, which is not exactly this or even close to this. It's somewhat away from this number. So that type of error can happen. It is only, physically speaking, it's a silly example, but it at least shows what the point of this advice is. that what can go wrong if this is not followed. However, if we do follow this advice in this same situation, then what will happen? Let us see. So this time we keep one more digit and that turns out to be 4. After 4 also there are other digits which had to be removed, and then we take its reciprocal and we see that this time we actually find 9.58 as the final answer. So we get back with what we started, and that is why we should keep one more digit than the number of significant digits in the least accurate measurement. So with this section, I should not perhaps say section ends, because after this there are some other things, but this measurements, errors, this part is over. The next thing that we have is dimensions of physical quantities. So we will see in the next video on physics what those things are and how they can be used to verify some physical equations, and there are some other things that dimensions can do for us. So see you in the next physics video on this same day next week. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.